So today we're going to continue 10.2. We're going to talk about the derivatives of parameterized curve, and we're going to use the definite integral to find the area. Well, let us begin by reviewing what we learned so far. Recall that. We say, hey, suppose you have a particle moving along a curve. And one of the points on that curve can be represented by using x and y. Remember that we said, hey, let us use a third parameter, like an angle, like time, like heat, different parameters to connect x and y to that new parameter. We said that, hey, suppose x is equal to f of t and y is equal to g of t. Well, after eliminating the third variable, like t, we could find a relation between x and y, like y equals to f of x. So now that we have a relation between x and y, we can talk about the derivative, the first derivative and the second derivative of this parameterized curve. Okay, so let us take the derivative of both sides. And remember that this depends on t. So here you have y of t equals to f of x of t. Or you can rewrite it this way. Y is actually g of t. So you have g of t equals to f of t. So the derivative on the left-hand side is going to be g prime of t. The derivative on the right-hand side, remember that for the derivative on the right-hand side, we have to use the chain rule. The chain rule gives you f prime of t times f prime of t. Now what I'm going to do, I'm going to divide both sides by f prime of t to find the relation between f prime and g prime and f prime. If f prime of t is not 0, then f prime of f of t is equal to, so the derivative of this function that is connecting x and y together is equal to g prime of t over f prime of t. So the derivative of that function depends on variable t. Okay, so note that dy over dx can be written as dy over dt over dx over dt. dy over dt, y is equal to g of t. The derivative of y with respect to t is g prime of t over the derivative of x with respect to t is f prime of t. Another formula. So dy over dx, or the first derivative of y with respect to x, is equal to g prime of t over f prime of t. Now I'm going to move on to find the second derivative. The second derivative of y with respect to x is equal to, now I want to separate these, d over. So let me write it here. Here I have d over dx of dy over dx. This is my formula. Then I show you how to use dt. I'm going to divide these two by dt. So I get d over dt of dy over dx divided by dx over dt. So when you have the first derivative, we can plug that in. to find the second derivative. This is equal to, so let me write this formula here for you. Divide this, the second derivative of y with respect to x is equal to d over dt of dy over dx divided by dx over dt. So what is dy over dx and how do we take the derivative with respect to t? On your numerator, you can use the quotient rule. You have your quotient rule. So the derivative of g prime is the second derivative of g times f prime minus the second derivative of f times g prime divided by the derivative of f raised to the second power, f prime of t to the second power, and dx over dt, dx over dt, the derivative of x with respect to t is f prime of t. So you can simplify this formula. You can write this as well. The second derivative of y with respect to x is equal to. On the numerator, you have the second derivative of g, first derivative of f, minus the second derivative of f, first derivative of g, divided by first derivative of f to the third power. So let us go over one example to feel more comfortable how to use these. Example. We are on page 2. So suppose you have a curve like C, which is defined parametrically using x equals to t squared and y, which is defined as t cubed minus 3t. Part A of the question says, show that C has two tangents. Show that this curve has two tangents at the point 3 and 0, and find the equations of those tangent lines. Well, okay. So what do we have here? We have a parameterized curve. What are we looking for? We're looking for tangent line. So recall that. Remember to write equation of any line, meaning y equals mx plus b. So m, the slope of the line, and the y-intercept. To find m, to find the slope, we need to take the derivative. Okay. In this case, we have a parameterized curve. We have nice formulas to follow. We know that dy over dx is defined as the derivative of y divided by the derivative of x. The derivative of y, remember that this is your gt and this is your f of t. The derivative of y is 3t squared minus 3 divided by the derivative of x is just 2t. There you go. So this is just the derivative. What I need m, or slope of the line. So to find m, to need slope, I need t, values for t. Now we need values for t. Do we have values for t? Unfortunately not. We have to find them. But how do we find them? We have a point with x equals to 3, y equals to 0. So what I'm going to do, I'm going to plug those in to the original equation to find my t values, since x is t squared and y is t cubed minus 3t, and x is equal to 3, y equal to 0. I get this as the equations to solve for t. So here 3 is equal to t squared. It means that my t is plus minus square root of 3. Then my y is equal to 0. So 0 is equal to t cubed minus 3t. It means that if I factor out t, I get t squared minus t equal to 0. So t is 0. T is plus minus square root of 3. How many options do I have for t? 3 options. So we have 3 options for t. T can be 0, t can be negative square root of 3, t can be positive square root of 3. Which one is acceptable? We have to look at our derivative. So this is the derivative of this curve, parameterized curve. If I plug in 0 on the denominator, I get 0. So it makes the derivative undefined. So dy dx is undefined. That's why I don't need t equal to 0. So my options are negative square root of 3 and positive square root of 3. So I need to write this equation. Y is equal to mx plus b. My t is equal to negative square root of 3. What is the derivative, or what is the first slope? M1 is equal to, so I have 3 times 3 minus 3 divided by negative 2 square root of 3, which is negative square root of 3. M2 is 3 times 3 minus 3 over 2 times square root of 3, which is square root of 3. I found M1 and M2. Now you just follow equation y equals to mx plus b, and you're done. So in this case, your y is equal to negative square root of 3 times x minus 3, the first tangent, and here you get y equals to m square root of 3, x minus x of 0, your x of 0 is equal to 3, x minus 3. Let us move on to the second part. Well, the second part of the question says, find points on C where the tangent is horizontal or vertical. Where tangents are horizontal or vertical. Okay, remember that when we're talking about tangent, we're talking about the first derivative of the function. So tangent is horizontal if the first derivative of the curve of the function is equal to 0 and tangent is vertical, or we have a normal line. If the first derivative does not exist. So by using what we got from part A, we know that dy over dx was, on the derivative, 3 t squared minus 3 divided by 2t. So you take the derivative, you set it equal to 0, and find t values such that those t values make this derivative equal to 0. It means that your numerator must be equal to 0. 3t squared minus 3 is equal to 0. So t squared minus 1 is equal to 0. T is plus minus 1. T is plus minus 1. It means that your x is 1, and you have 2 options for your y. When t is 1, you get -2. When t is -1, you get +2. And the tangent is vertical or normal when the first derivative of the function doesn't exist. Doesn't exist, it means that when you look at the derivative of the function, the denominator is equal to 0. So since we have a rational expression, we set the denominator equal to 0. So 2t is 0, t is 0, it means that your x is 0 and your y is 0. So at the origin, you get a normal line. At 0 and 0, we have a normal line. Well, part C is asking about concavity of the graph.
Professor, can you hear me?
Yeah. So part C says, analyze the concavity of this curve. Concavity of C. So remember that you learn when you're talking about concavity, we need the second derivative. If the second derivative is positive, the graph concave up. If the second derivative is negative, the graph concave down. So we need to work with the second derivative of this curve. We already know that the first derivative, dy over dx, is defined as 3t squared minus 3 divided by 2t. Now we have to take the second derivative. Let's follow the formula. The second derivative is equal to d dt of the first derivative, 3t squared minus 3 divided by 2t divided by dx over dt. So before taking the derivative of the first expression here, I'm going to simplify it a little bit more. D over dt. I have 3 halves t minus 3 over 2t divided by dx over dt. Well, dx over dt is super easy because you're taking the derivative of x with respect to t. It is just 2t. Here, the derivative of 3 halves t is 3 halves minus the derivative of 3 halves times t gives you -3 over 2t squared. Okay, the second derivative is equal to. So here you have 3 halves plus 3 halves t squared divided by 2t. So here you can factor out 3 halves and then multiply it by 2, you get 3/4. And here you get 1 over t plus 1 over t cubed. I'm trying to just do the algebra and simplify it as much as I can because it helps me to analyze the second derivative easier. So I get 3 over 4 t squared plus 1 over t cubed. Okay, what is the sign? This is my question. What is the sign of the second derivative? Guys, note that the numerator is t squared plus 1. It's always positive. So since t squared plus 1 and 3 over 4 are positive, we only care about t cubed. T cubed is the deciding factor on the sign of this rational expression. So if you set the t equal to 0, the second derivative doesn't exist, but it helps us to separate the sign of the second derivative. T equal to 0, the second derivative doesn't exist. If I plug in again any negative number into the second derivative, this quantity is going to be negative. So from negative infinity to 0, I have a concave down graph. And if I plug in any positive t here, 1, 2, 3, 4, anything, the sign of the second derivative is going to be positive. It means that I have concave up behavior for this curve. So from 0 to positive infinity, the graph concave. Well, let us talk about the area below the graph of a parameterized curve. We are getting back to Math 1B. So remember that in Math 1B, you learned about the area. The area below the curve of a function like y equals to, let's say, f of x, when x is bounded between a and b. Suppose to visualize it this way. This is your x-axis, this is your y-axis. Yeah, suppose here you have your graph. This is your y equals to f of x, and you want to find the area below the curve of the function bounded between y and x equals to a, x equals to b. The area is defined using a definite integral. So your area is equal to a, which is the integral, the definite integral. X is bounded between a to b of y dx. Well, now you have a parameterized curve. For a parameterized curve, x equals to f of t and y equals to g of t when t is bounded between alpha and beta. Guys, since we have a parameterized curve, we need to write this integral in terms of t. So the area is equal to, your x was bounded between a to b, your t is bounded between alpha and beta. What is y? Y is g of t. I'm writing everything in terms of t. That's why the boundary, instead of being a to b, is alpha to beta. gt and dx, it means that I have to take the derivative of x. I get f prime of t dt. This is the formula. A is equal to alpha to beta, g of t, f prime t, dt. So this is the math behind it, how to get from the definite integral for y equals to f of x to a parameterized curve equation. One example for you. Example says, well, find the area under one arc of cycloid which is defined as x equals to r theta minus sine theta, and y is r 1 minus cosine theta, and theta is in between 0 to 2 pi. We want to find the area under one arc of this parameterized curve. We have a nice formula to follow. Area is equal to the integral. My theta is in between 0 to 2 pi. And r is just a scalar. We don't need a new variable. R is just a scalar. gt, remember that. G is your y. So let's copy this down. R 1 minus cosine theta. So this is my y. And now I need my f prime of t dt. It means that I need my dx. Remember that this piece here is your dx. So whatever your x is, you have to take the derivative of x and write it here. So r stays the same. R is just a scalar. The derivative with respect to theta is 1. The derivative with respect to theta is cosine. And you need d theta. So this is your dx. Well, the rest is easy. You've seen this before in Math 1b. A is equal to integral 0 to 2 pi. R times r is r squared. I can write r outside the integral. And I have 1 minus cosine theta, 1 minus cosine theta, d theta. So let us multiply these two. I get r squared, 0 to 2 pi, 1 minus 2 cosine theta plus cosine squared theta, d theta. Okay, taking the integral of 1 is theta, so this is r squared theta minus, here you get 2 sine theta. And to take this integral, let us convert cosine squared of theta, 1 plus cosine 2 theta divided by 2. I'm using this formula because I have exponent 2 and I have to simplify it as much as I can. So I have a half plus cosine 2 theta divided by 2. So the integral of 1 is theta, the integral of 2 cosine theta is 2 sine theta, and here I left with the integral of a half is theta over 2. The integral of cosine 2 theta is sine 2 theta divided by 4, and my theta is in between 0 to 2 pi. So let us plug in 2 pi, then let us plug in 0. You shouldn't be worried too much about 0. Why is that? I have theta here, sine of 0 is 0. I have theta here, sine of 0 is 0. So you can just basically ignore theta equal to 0. Let us plug in 2 pi, you get r squared, 2 pi minus 0 plus 2 pi over 2 plus 0. So here you have 3 pi r squared. This is the area.